We tend to look at the night sky as if it were a map drawn for us, a quiet suggestion that, given enough time and better machines, every distant point could eventually be reached. This belief has been reinforced for decades, not by observation, but by imagination. Stories have trained us to think of the Milky Way as a navigable expanse, where distance is merely an engineering problem waiting to be solved. But there is a fundamental error hidden inside that assumption. The Milky Way is not an ocean to be crossed. It is not even a landscape in the ordinary sense. It is a structure of such scale that our usual ideas of travel begin to lose meaning. When we casually speak about going to another star, we are compressing distances so extreme that the language itself becomes misleading. A useful teaching insight here is this: human intuition evolved to understand kilometers, not light years. When the scale changes by factors of trillions, intuition does not stretch with it. It breaks. Consider how we approach exploration on Earth. Every journey we have ever made, from the earliest migrations to modern aviation, assumed that destinations remain relevant within a human lifetime. Progress, in this sense, has always been tied to time we can experience. Now, extend that expectation to a galaxy that spans roughly 100,000 light-years across, and the assumption quietly collapses. The problem is not simply that the Milky Way is large, it is that its size disconnects distance from human timescales entirely. Travel is no longer a question of speed alone. It becomes a question of whether arrival has any meaningful definition left. This is where the comforting illusion begins to dissolve. What we have imagined as a frontier is, in reality, a boundary imposed by the laws of physics and the limits of time itself. So, before we continue with ideas of engines, propulsion, or advanced technology, we must first correct something more basic. We need to recalibrate how we measure space, not with emotion or imagination, but with proportion. Because until we understand the true scale of what we are dealing with, every solution we propose will be built on a misunderstanding. And that raises a more precise question, one that will guide everything that follows. What does it actually mean, in measurable terms, to cross a galaxy? We must first correct the scale we are using. At human scale, distance feels intuitive. A kilometre can be walked, a city can be crossed, and even continents can be traversed within days. But this intuition becomes unreliable the moment we step beyond our immediate environment. The difficulty is not that space is large, but that it is large in a way that our minds are not designed to grasp. So let us rebuild our sense of proportion using a controlled model. Imagine compressing the entire solar system down to the size of a small coin. The Sun, the planets, even the orbit of Neptune, all contained within that tiny circle. Now, in this same model, where would the nearest star be located? Not across the room. Not even across a city. It would be roughly 100 meters away. This is a useful teaching moment. Even when everything is reduced to a scale we can visualize, the separation between stars does not shrink into convenience. It remains vast, disproportionately so. The space between systems is not filled with pathways or intermediate stops. It is overwhelmingly empty. Now extend this same model further. If each solar system is a coin, separated by distances measured in hundreds of meters, then the structure containing billions of such systems becomes difficult to contain within ordinary geography. The Milky Way, under this scaling, would stretch across something comparable to an entire continent. What appears in the night sky as a dense band of light is, in reality, a sparse distribution of stars separated by enormous voids. The brightness we observe is not density, but accumulation along a line of sight. This leads to an important clarification. Space is not crowded, it only appears so from a distance. In practical terms, it behaves less like a forest and more like an arid desert, where points of interest are separated by distances that dominate everything else. A brief factual anchor helps here. The nearest star system, Proxima Centauri, is about 4.24 light-years away. That is over 40 trillion kilometers. Numbers of this scale are not just large, they are operationally limiting. So the image of exploration must be adjusted. We are not standing at the edge of a navigable ocean. We are confined within an isolated pocket, separated from the next by distances that resist traversal in any meaningful time frame. And once this corrected scale is accepted, the next step becomes unavoidable. If the distances are this extreme, then the question is no longer whether we can imagine crossing them, but whether any technology we possess can function within such constraints. Once this scale is accepted, the next logical step is to test it against reality. Not imagination, not theoretical speculation, but the best capability we currently possess. Let us consider the fastest machine humanity has ever built, NASA's Parker Solar Probe. Designed to study the Sun, it reaches speeds close to 700,000 kilometers per hour. By any terrestrial standard, this is extraordinary. At such velocity, one could circle the Earth in minutes. But the usefulness of speed depends entirely on the scale over which it is applied. If we project this speed outward, beyond our solar system, and into the structure we have just defined, the numbers change character completely. At 700,000 kilometers per hour, crossing the Milky Way would require approximately 1.7 billion years. A brief comparison helps anchor this. The Earth itself is about 4.5 billion years old. That means such a journey would take more than a third of the entire history of our planet. A teaching insight is worth noting here. When time spans reach into hundreds of millions or billions of years, they stop functioning as durations and begin functioning as geological eras. They exceed not just human lifetimes, but the continuity of species. Consider a simple thought experiment. If such a journey had begun at a time when life on Earth consisted only of microscopic organisms, it would still be in transit for a significant portion of that history, only now approaching its destination. This is not a limitation of engineering refinement. It is not a matter of building a slightly faster engine or improving efficiency. The gap between our capabilities and the requirements of galactic travel is not incremental, it is absolute. Speed in this context does not scale in a way that preserves usefulness. Increasing it within known technological bounds produces negligible impact on outcomes measured across galactic distances. So we arrive at a necessary conclusion. Our most advanced machines, impressive as they are within the confines of our planetary system, fail entirely when evaluated against the structure of the galaxy. And this naturally leads to the next question. If even our fastest technology is insufficient, could the fundamental limits of physics itself offer a solution, or do they impose an even stricter boundary? If technological progress fails at this scale, the next step is to examine the ultimate limit imposed by nature itself. Not a machine, not an invention, but a boundary written into the structure of the universe. This boundary is the speed of light. According to Einstein's theory of relativity, no object with mass can reach or exceed this speed. It is not a challenge to be solved, but a rule to be respected. Every increase in velocity demands more energy, and as an object approaches the speed of light, the required energy rises toward infinity. But for the sake of understanding, let us momentarily set aside this constraint and assume something unrealistic. Suppose we could travel at light speed. Even under this ideal condition, the result is not what intuition suggests. Crossing the Milky Way would take approximately 100,000 years. A useful comparison helps clarify this. Human civilization, from the earliest agricultural societies to the present day, spans roughly 10,000 years. In other words, a single journey across the galaxy would last 10 times the entire history of organized human life. This introduces a different kind of limitation, one that is often overlooked. Travel is not only about reaching a destination, it is also about continuity between departure and arrival. If that continuity is broken, the concept of a journey begins to lose coherence. Consider a simple teaching example. If a message is written today and delivered after 100,000 years, it no longer connects 2 points in a meaningful way. The sender and receiver do not share a common context. The information arrives, but the relationship is gone. The same principle applies to physical travel. A civilization that begins such a journey would not be the same civilization that completes it. Languages would change, cultures would disappear, and even the purpose of the mission could be forgotten. So the issue is not merely that light speed is difficult to achieve. It is that even if it were available, it does not solve the deeper problem. Time itself becomes the dominant barrier, and once time enters the discussion at this scale, the the implications extend beyond travel. They begin to affect communication, coordination, and the very possibility of maintaining a connected system across the galaxy. Once time becomes the dominant constraint, its effects extend beyond travel and begin to disrupt something even more fundamental: communication. Let us examine this carefully. If a signal is sent across the Milky Way at the fastest possible speed, it will still take approximately 100,000 years to reach the other side. This is not a delay in the ordinary sense. It is a separation so extreme that cause and response lose their connection. A useful teaching example clarifies this. Imagine sending a letter that will be read 100,000 years from now. The language in which it was written may no longer exist. The cultural references would be unintelligible. Even the reason for sending the message could be lost. The information arrives, but its meaning does not. This is the condition imposed by galactic distances. Now consider what this implies for any form of coordinated system. An empire, by definition, requires the ability to issue instructions and receive responses within a meaningful time frame. Without this exchange, authority cannot be maintained, and structure begins to dissolve. If a command takes 100,000 years to arrive, it no longer functions as a command. It becomes a historical artifact. By the time it is received, the originating system may have changed beyond recognition or ceased to exist entirely. The same applies in reverse. Any response sent back would take another 100,000 years. What returns is not a reply, but a fragment of a past that no longer connects to the present. This leads to an important clarification. Distance in space does not merely separate locations, it separates moments in time. Each region of the galaxy becomes isolated within its own timeline, unable to synchronize with others in any practical sense. A brief, factual perspective reinforces this. Even communication between nearby stars involves delays measured in years. Across the full diameter of the galaxy, these delays expand to scales that exceed the lifespan of civilizations themselves. So the limitation is not technological inefficiency, it is structural. The universe enforces a delay that prevents the formation of any unified galaxy-wide system. And once communication fails at this level, the implications deepen further. If coordination across distance is impossible, then the next question is unavoidable. Are there even physical methods that could overcome these constraints, or does the problem extend into the fundamental limits of energy itself? If communication fails across these distances, the next question becomes more fundamental. Are we limited by our current technology, or are we constrained by the laws that govern the universe itself? To answer this, we must examine the relationship between speed and energy. In classical thinking, increasing speed is a matter of applying more force or improving efficiency. But at relativistic scales, this relationship changes completely. As an object with mass accelerates, its effective inertia increases. Each additional increment of speed requires disproportionately more energy than the last. A useful teaching insight is this. Approaching the speed of light is not like climbing a hill with a steady slope. It is more like approaching a vertical wall. The closer you get, the harder progress becomes, until further movement is no longer physically achievable. Mathematically, the energy required to reach light speed diverges toward infinity. This is not a technological barrier that can be engineered around. It is a physical boundary built into the structure of space-time. Even if we consider optimistic future propulsion systems, such as antimatter engines or advanced fusion drives, the projections remain limited. These concepts may allow velocities approaching a fraction of light speed, but not the limit itself. Let us take a generous estimate. Suppose a spacecraft could reach 10% of the speed of light. This would represent a technological leap far beyond anything currently achieved, yet even at this velocity, crossing the Milky Way would require approximately 1 million years. It is important to pause on this number. Not centuries, not thousands of years, but 1 million years. This duration exceeds the entire span of recorded human history by 2 orders of magnitude. A brief comparison helps clarify the scale. 1 million years ago, early humans were only beginning to use primitive tools. Agriculture, cities, and written language did not exist. Project that same duration forward, and it becomes clear that no current human framework can remain stable over such a timescale. So, the limitation is no longer about speed alone. It is about the energy required to sustain that speed and the time required for it to have any meaningful effect. At this point, the conclusion becomes unavoidable. Physics does not merely make interstellar travel difficult, it enforces a form of isolation, and if journeys must extend across such immense durations, the problem shifts once again. It is no longer only about reaching a destination, but about what happens to those who attempt the journey over time. If journeys must extend across such immense durations, then the problem changes form. It is no longer only about propulsion or distance, but about continuity of life itself over time. This is where the concept of a generation ship emerges. A generation ship is not simply a vehicle. It is a closed, self-sustaining environment designed to support human life across thousands or even millions of years. The original travelers would never reach the destination. Instead, their descendants would continue the journey, each generation inheriting a mission they did not begin. At first, this appears to solve the problem of time. If individuals cannot survive the journey, then a continuous lineage might. But this introduces a deeper and less intuitive challenge. A useful teaching insight is this: biological and cultural systems are never static. They evolve continuously, even under stable conditions. When stretched across extreme timescales, this evolution becomes profound. Consider language as a simple example. Over just a few thousand years, languages diverge so significantly that mutual understanding becomes impossible. Extend this to 10,000 years, and original meaning is almost entirely lost. Over 100,000 years, history itself becomes indistinguishable from mythology. Now, extend this process further, across a million-year journey. The descendants aboard such a ship would not simply speak differently or think differently. Their biological characteristics could also shift. Small genetic variations, accumulated over countless generations, would gradually reshape the population. A brief factual perspective helps clarify this. Evolution does not require dramatic environmental change. Even isolated populations on Earth demonstrate measurable divergence over far shorter timescales. Over a million years, this divergence becomes unavoidable, so the mission transforms. What begins as an attempt to transport humanity across the galaxy becomes a process that alters humanity itself. The individuals who eventually arrive would not share the identity, culture, or possibly even the biological traits of those who initiated the journey. The connection between origin and destination would exist only as distant, reconstructed memory. This leads to a critical conclusion. A generation ship does not preserve a civilization. It creates a new one in isolation. And once this transformation is understood, another complication becomes visible. Even if such a civilization survives the journey, there is no guarantee that the destination they were aiming for will remain the same by the time they arrive. Even if we assume that such a journey can be sustained, and that a civilization can survive the passage of time, another constraint emerges that is less intuitive but equally decisive. The destination itself is not fixed. When we observe the night sky, we tend to interpret it as a stable arrangement of stars. Constellations appear unchanged across generations, giving the impression of permanence. But this is an illusion created by the limitations of human timescales. In reality, the Milky Way is in constant motion. Every star is orbiting the galactic center at immense velocities, often hundreds of kilometers per second. Over long durations, these motions accumulate into significant positional changes. A useful teaching insight is this: space is not a static map, but a dynamic system. Any attempt to navigate it must account not only for where objects are, but where they will be when you arrive. Now consider the implications for a journey lasting hundreds of thousands or millions of years. The coordinates selected at departure are based on observations made in the present, but those observations are already delayed. Light from distant stars takes years, sometimes thousands of years, to reach us. This means we are never seeing objects as they are, but as they were. A brief, factual example clarifies this. If a star is observed at a distance of 50,000 light-years, the image we receive today represents its state 50,000 years in the past. Any movement, transformation, or destruction that has occurred since then is unknown to us. So, when a trajectory is planned, it is effectively aimed at a historical position, not a current one. Over the duration of a long journey, the target star may have shifted significantly along its orbit. In some cases, it may have undergone catastrophic events such as supernova explosions, altering or eliminating the system entirely. This introduces a fundamental navigational problem. The longer the journey, the greater the uncertainty in the destination's future state. So even if a civilization overcomes distance, time, and energy, it still faces a final complication. It is not traveling toward a fixed point, but toward a moving and partially unknown target. And this naturally leads to a deeper realization. If our knowledge of distant locations is always outdated, then the very act of aiming across the galaxy is based on information that is already incomplete. And once we accept that the destination itself is uncertain, a deeper limitation begins to emerge, one that affects not just movement, but knowledge itself. Every observation we make of the universe is delayed. This is not a technological flaw, it is a fundamental property of light. Information travels at a finite speed, and that speed defines how we perceive reality. When we look at distant objects, we are not seeing them as they exist now, but as they existed when their light began its journey. A useful teaching insight is this. In astronomy, distance is equivalent to time. To look farther away is to look further into the past. Consider a star located 80,000 light-years from Earth. The light reaching us today left that star 80,000 years ago. During that time, entire civilizations on Earth have risen and disappeared. Yet for that star, we are still observing a moment frozen in a distant past. This creates a profound limitation for navigation. Any attempt to travel towards such a star is based on outdated information. We are not targeting a current location, but a historical one. A simple analogy helps clarify this. Imagine trying to meet someone using a photograph taken tens of thousands of years ago. The person may have moved, changed, or no longer exist. The image provides information, but not certainty. The same principle applies on a galactic scale. A civilization may direct its efforts toward a star system that appears stable in observation. But during the time it takes to reach that system, it may undergo transformations that are completely invisible from the point of origin. Planets may shift, stars may evolve, and in extreme cases, entire systems may be destroyed. This introduces a form of blindness into long-distance travel. Not because we lack instruments, but because the information those instruments provide is inherently outdated. So crossing the galaxy is not simply a challenge of distance or time, it is also a challenge of knowledge. We attempt to navigate toward destinations that we cannot observe in their present state. And once this is understood, a final implication begins to take shape. If every distant point in the galaxy is observed as a fragment of the past, then any attempt to connect with it is, in a very real sense, an attempt to reach something that may no longer exist in the form we expect. This brings us to a broader question, one that extends beyond travel itself. If the universe enforces such isolation through distance, time, and delayed knowledge, what does this imply about the existence of other civilizations and our ability to ever encounter them? And when all these constraints are considered together, distance, time, energy, motion, and delayed knowledge, a broader pattern begins to emerge. It is not simply that travel across the galaxy is difficult, it is that the structure of the universe appears to prevent meaningful connection at that scale. This observation leads directly to a question that has occupied scientific thought for decades. If the galaxy contains billions of stars, many of which are older than our Sun, then statistically, intelligent life should not be unique to Earth. Given sufficient time, some of these civilizations should have developed technologies far beyond our own. And yet, we observe no clear evidence of their presence. This tension is often summarized as the Fermi paradox. If intelligent life is common, why have we not encountered it? A useful teaching insight here is to reconsider the assumption behind the question. It assumes that advanced civilizations should be able to spread, communicate, and leave detectable traces across the galaxy. But everything we have examined suggests that such expansion may not be physically practical. Distance isolates, time disrupts continuity, energy imposes strict limits, information arrives too late to be useful. Even destinations themselves are uncertain. When these factors are combined, they do not merely slow progress. They fragment the galaxy into separate regions, each effectively cut off from the others. A simple analogy helps clarify this. Imagine a vast ocean where every island is separated not by water, but by time. Delays so extreme that no message can arrive before the sender is gone. Each island may host life, culture, and intelligence, but none can meaningfully interact with another. This may be the true structure of our galaxy. Civilizations could exist in large numbers, each developing independently, each reaching its own understanding of the universe, yet all confined within their own region of space-time. Not because they lack intelligence or ambition, but because the laws governing the universe impose a form of natural isolation. So, the absence of evidence may not indicate absence of life, it may indicate absence of connection. And this leads to a final, precise conclusion. We are not necessarily alone. We are simply separated by distances and timescales that make interaction effectively impossible. The night sky, then, is not a map of destinations waiting to be reached. It is a record of distant events, a collection of signals traveling across immense spans of space and time. Each point of light is not an invitation, but a reminder of the limits within which we exist. A universe vast enough to contain countless possibilities, yet structured in such a way that each remains, in practice, unreachable.